On where you are in the world, good afternoon, good morning, or good evening. Welcome to this global webinar on the series of Future Ready, and in particular resilience. How do you take factory production-like methods and deploy them efficiently on site to raise the productivity of construction? That's the Future Ready topic that we're considering in today's presentation about modular offsite bridge substructures. Before we get going, just a couple of housekeeping items. So firstly, if you do want to see a copy of the PDFs of the presentation, you can download that from the sidebar in the GoToWebinar panel. So if you go to handouts, then you have the opportunity to download a PDF of the presentation. The second point of housekeeping is if you do have questions, and we'd love to hear your questions at the end, there's a questions panel in the sidebar. Please put them in there and we will pick them up at the end of the presentation. So my name is Mungo Stacy, and I'm the head of profession for the Civil Bridge and Ground Group in the UK. I'm joined by my colleagues, Gbenga Oludotun and Angel Ortega, and we're going to talk you through WSP's future-ready approach to modular offsite substructures for bridges. There are elements of what we'll talk about today which are proprietary. So the system, of which you see an image on the screen, was developed by us working in collaboration with the contractor Lang O'Rourke. So they own the intellectual property on the system. However, we as WSP own the intellectual property on the engineering tools which made it possible. And we'll talk about both of those aspects, both the system and the tools which are capable of being transferred to other projects. In terms of the structure of today's presentation, I'll give you a brief introduction and sow the seeds of how this project fits with WSP's Future Ready themes. I'll hand over to Gbenga, who will talk about the development of the modular bridge substructure products. Angel will then talk about WSP's parametric modeling tools and how that has been used in this digital bridges project. And I'll then finish off with a bit of an insight into the future direction for this system. And then we'll pick up with some questions and answers. So this is me. I'm head of profession for Civil Bridge and Ground in the UK. Working at WSP, you're obviously all familiar with the Future Ready theme and how that's considered in the 4 areas around society, climate change, resources, and technology. Just thinking through those and how those drive this particular project. Under society, we have increasing demands to keep our transport networks open to minimize disruption during construction and maintenance. There's also a drive to increase the health, safety, and well-being of our workforce. And the image down at the bottom shows one of the advantages of moving to off-site construction. It means that rather than having people crouching over in the heat or the cold or the rain on site, we can fix reinforcement in a controlled environment in the factory with improved well-being, but also potentially higher quality to the products. Under climate change and resources, these are hot topics at the moment. In many areas of the world, WSP is launching initiatives around achieving net zero. Certainly in the UK, we've launched an initiative to reduce the carbon content from our designs and advice by 50% over the next 10 years. And reducing the quantity of resources in the designs that we create is a key step in trying to achieve that. That might mean that we need to start optimizing our designs against multiple constraints to minimize material use, maybe not just considering cost, but also the carbon content. And then the final Future Ready set of themes is around technology, and these can include advances in construction technology, such as the craneage, which makes larger offsite components possible, and also the digital enablers, which can help us to optimize against multiple constraints. And we'll be focusing very much on those digital enablers during this presentation. So I'll hand over now to Gbenga, who will talk you through the development of the modular product system.
Thank you, Mungo, and good afternoon, everyone. My name is Oludotun, the associate in the UK. I'm going to give you a very high-level overview of the substructure bridge products that we've developed. But you might be wondering, why the focus on substructure bridge products? Well, building structures, which are called, referred to as vertical assets, have progressed quite quickly in terms of offsite construction adoption than bridges, which go referred to as linear assets. With bridges, you've been able to standardize the superstructure elements with the beams, but the abutments, the vertical elements, have not been able to be adopted to suit offsite manufacturing, as you will find with building structures where you have the beams, the slabs, the columns all being pre-manufactured and installed on site. So a few lessons were learned on the previous substructure elements on a few bridges. So we had a look, the team had a look at the abutments and wondered how it was possible to be able to prefabricate them and install them in a rapid construction manner on site. The abutment shells I'm going to talk about were the next evolution of that design for manufacture and assembly concept. Moving along, please. So what are the modular bridge substructure products? They're essentially reinforced concrete shells, precast of course. And there are three variants: single, double, which you can see on screen, and triple core variants. They are 2 meters high, 1.7 meters deep, and have a thickness of about 200 millimeters. The single, double, and triple are all in variants of 2 meters, 4 meters, and 6 meter lengths. They're essentially structurally non-participatory permanent formwork, which are arranged vertically one above each other. And this allows the core to be infilled with reinforced concrete. And this also brings up the possibility of using different forms of concrete within the core, because you no longer have to strike the formwork and to have the strength for the abutment. Moving along, please. So how were these products developed? As Mungo earlier mentioned, we collaborated with Langerock, who are the contractors and also the precast manufacturers, and also with Rambo, who are designers, through a series of design workshops. And I still remember that day when we started with a blank sheet of paper to talk about how do we approach substructure development with all what we've learned from the previous iterations. And these conversations had to pick up items around durability, buildability, standardization, quality, and all different elements that you would have if you need to put all this together. And Langerock, with their knowledge, experience on building prefab products, were able to bring their expertise into it. The products were then applied on various light projects. Two I will name: the HS2 Phase 1 enabling works, which are hybrid structures, and East West Rail Phase 2, which takes a rail line across the Bletchley West Coast Main Line around Bletchley. I'd like to take you to have a look at this picture on the right, because you'll see how the final product matches what we have in the BIM environment. So we'll move on, please. Right, so as I earlier stated, the precast shells begin in the BIM environment, where they're all arranged to create the abutment at the right height, to the right length with the wing wall and the abutments. And once that is done, the information is then sent to the Explore manufacturing plant to produce all the shells. Being in the BIM environment, all the shells are all tagged and they all have IDs, so they all know where they're all meant to be installed exactly on site. So as you can see, they're all manufactured and placed onto a flatbed truck, which does not require any escort on the highway network in the UK, and they're delivered onto site just in time. And the crane just lifts it off the truck and places it right above the starter bars, as you can see, off the pile cap base. And this process is continued until you then have the final product on the bottom right, which shows the finished look of the abutment with precast beams already installed. Moving on to the next slide, please. So after the proof of concept that this was possible, Langerock won an innovation fund from Highways England to then develop a digital bridges configuration tool. This tool, which is owned by Langerock, essentially uses the modular precast products and arranges them to create a bridge. So we have the precast beams, we have the precast shells, we have L walls, and we have N2 parapets or H4A parapets, high impact parapets, which are then assembled in a digital space and checked for the right configuration of the project. And that is more of a scheme design to show that the elements can all work together. This then necessitated a certification of the standardized products, that is not just the shells alone, but all the other parts of it, including the L walls, to provide assurance and that it can be adopted by other parties. The tool is applicable to quite a high percentage of typical bridges. If you look at the graph below, showing the current tool range of 0 to 30 degree skew and 0 to 40 meter spans, and the intention in future is to increase that range from 40 to 65 meters and up to 60 degree skew, and not just looking at a precast, pre-stressed concrete beam single span, but looking at also including steel composite multi-span structures. Next slide, please. So the digital configuration tool, as I mentioned, it essentially prepares a scheme design and also produces technical approval documents along with cost estimates. On screen, on the bottom right, you can see the GA drawing, which is produced straight out of the tool based on the configuration that the designer will input. And the other two screenshots show the interface of the tool where you all slide the different parameters of headroom, of skew, of span, and you can check the structure as you're progressing to ensure it fits within the space and boundaries you've set. And an engineer can easily do this. But then you might wonder, how on earth does a tool know which particular configuration is actually feasible or not feasible? Well, this was possible by using a lookup table of over 1,000 bridge configurations. If you remember the graph previously, 0 to 30 degree skew, 0 to 40 meter span. So we had different configurations within that space and created a lookup table, which the tool then uses to determine which particular configurations work and which doesn't. And so you might wonder, how on earth were we able to analyze over 1,000 bridge configurations? Well, I'd like to hand you over now to Ankel to talk about the parametric tool.
Afternoon, everybody. My name is Ortega. Moving on to the next one. Next slide. So I'd like to talk you through WSP's involvement in the development of the bridges configuration tool. So the client asked us to undertake a parametric study that consisted of 1,000+ bridge configurations that are defined by variables parameters like skew, span, ground conditions, and by combining these ones, these variable parameters, you get those 1,000+ bridge configurations. So we went ahead and we undertook that parametric study, and we summarized the outcome in a lookup table, which concluded what for each of these bridge configurations, which were viable and which weren't viable. This is what you see in the screen, this flat lookup table that Gbenga was talking about. That is our deliverable for the bridges configuration tool, and that sits behind the bridges configuration tool and very much at the heart of it. So how do we go about undertaking 1,000+ analysis configurations, which one of them would typically take 2 weeks? Each of them, you would need 4 years to undertake this. So we developed an automation workflow that I will now talk you through. Next slide, please. In this slide, you see the idealized diagram of our finite element structural model. Straight away, you can make the connection. Okay, I've got 1,000+ bridge configurations. I'm going to need 1,000+ of these models. This is where parametric modeling comes in. If you think of that model, all of the points in there, as instead of being defined by absolute coordinates, all of those coordinates are there's relationships between them, and that allows us to build all those very different models which are controlled by the parameters and varying those parameters. This is a very quick introduction to parametric modeling. Next slide, please. Other key aspects of our automation workflow, other than parametric modeling, were compatibility. So we wanted to limit the number of software applications that we were using to avoid any interface issues. So we ended up using 2 software applications, Excel and Lucis, which is our finite element analysis software. We also used 2 programming languages, but from the same family, which are Visual Basic script and Visual Basic application. Second key aspect is modularity. We built our workflow in modules, so we could actually plug in and plug out the different modules. This allows us to do a lot of testing during the development phase. It also allowed us to progress work in parallel, and it also played a huge role in computational speed, which is our third aspect. Computational speed was critical here. If we think hypothetically that the workflow for one bridge configuration would take 1 hour, if you were to do those sequentially, it will take around 40 days. So through a combination of good programming techniques, we dropped that workflow for one single bridge configuration to around 30 minutes. And we also took advantage of the modularity nature of our workflow to run multiple bridge configurations in parallel using remote desktops in our offices. The result of doing this is that we could actually do around 200 models a day, completing those 1,000 bridge configurations in around 5 days. Next slide, please. You can see here our automation workflow. I don't have time to go in detail, but you can see the 3 main stages: input data, model generation and solving, and post-processing, which included extraction of results from the models and the design checks. Next slide, please. This is a brief video demonstration. Here you can see the input spreadsheet that we were using to input all of the parameters like the skew, the ground conditions, the skew angle, and you could also see on the right the actual script. What you can see right now is LUSIS, our finite element structure analysis, and we've actually run the script and is reading all of these input data from the Excel sheet in preparation for the building of the model. It will now start building this model. It will start with the geometry, and it will then add all other attributes like section properties, supports, loading. It would also build the load combinations, and it will also now solve it all in preparation for the next stage, which is the extraction of results and design checks. On a quick look, you can see, well, this is really powerful. You can build a lot of different models in a matter of hours, but that leads me nicely to the next slide, which is quality. If you make a mistake in that workflow, that will propagate throughout all of the different models. So quality was of the utmost importance. We had a 3-pronged approach for quality. So we were in partnership with Rumble, another engineering consultant, and we undertook independent checks on our work. Next slide. We undertook manual spot checks on selected models during the development phase. And then the 3rd prong will be automated checks that we developed that were undertaken on all of the models. Combining all these 3 aspects, we gain confidence in the output coming out of our design workflow. I will now pass it on to my colleague Mungo again.
Great, thanks Gbenga and Angel for that detailed description of the modular system and then the parametric modeling that we've done. So just to conclude, I want to round out with some ideas around the future direction. So the configuration tool as it currently stands is capable of configuring around 25% of the bridges in the UK market. So the tool accommodates single span bridges with pre-stressed concrete beams in the span range 0 to 40 meters. The intention over time, working in partnership with the funder and with the contractor, is to try to grow that to around 80%. And we already have identified several next steps about expanding out the product range, incorporating steel beams, working up to multi-span bridges. And just to look back to the future ready themes, I set the scene in terms of those societal demands about being able to build bridges quicker to avoid the disruption to our transport networks. Certainly the modular solution enables that. Approximately, we can save 1 month per bridge in the time for building the substructure. I also talked about the well-being advantages of moving the workforce from the construction site to the factory, the more controlled environment. I touched on the climate change and resources and the need to optimize our designs. Having this capability to run many different cases allows us to test our designs, possibly against multiple criteria. So rather than just going for the cheapest bridge, can we optimize against both the cost, but also possibly the carbon content of our structures or other metrics that we're interested in? And then finally, the technology. We talked extensively about the parametric modeling, and this way of automatically building models, developing many models in parallel is what our systems are now capable of. And the challenge really for us as a consultant is to see how we can best offer services to our clients based on the use of such technology. So that brings me to the close of our formal part of our presentation. Please, if you have got questions, please do put them into the questions panel and we will start handling those now. We'll also turn on webcams now so you get to see us. Hopefully that won't deteriorate the audio or the video quality too much.
Perfect. Thank you. Thank you, Tim, for a fantastic presentation. So before moving into the Q&A period, I would like to remind attendees to enter questions, like Mungo just mentioned, and also you can download the PDF version of the presentation from the handout box on the dashboard. We'll move to the first question. How do we reduce the risk of operational accidents during segment installation?
Hi, thanks, Sharon. I think I'll take that one first off. So I mentioned earlier that this is a commercial system. So we've been working together with Laing O'Rourke, they have the manufacturing facility. Gbenga mentioned the certification of the complete system to give that increased assurance to those working with the system. And part of that certification includes an installation manual and an approved installer scheme. So part of the criteria for being able to use the system is to go through this approved installer scheme. That covers things like the criticality of the tolerances. You saw on the early picture that these precast shells actually have to drop down over the starter bars coming out from the pile caps. So control of those tolerances is obviously a fundamental part of use of the system. And likewise, that approved installation scheme includes the various criteria around safety during the installation. But equally, the plus side of using a system such as this, the whole efficiency angle, is that rather than each bridge being bespoke and unique, actually over time the construction crews should become familiar with the use of the system. They're deploying exactly the same pieces from project to project. So over time, in theory, we should see a reduction in safety incidents and quality incidents because of that familiarity with the system and the repetitious nature of it. So that's one of the advantages and the drivers towards using modular precast offsite systems, is that you have those factory-like production systems and moving them onto the construction site.
Thank you. Next question. Are the elements supplied readily by mainstream suppliers?
Again, I'll take that one myself, and hopefully the next question we can direct to one of my other presenters. And it's actually a similar response, and it's part of the certification that the plan and one of the conditions of funding was to avoid creating barriers to competition. So the way that that's being addressed is by licensing the production of these units. So in the very early days, Gbenga mentioned having those initial workshops with Laing O'Rourke and thinking, what does this system look like? In the very early days, there are also discussions around, what is the unique selling point? What's the commercial angle here? And actually, they decided in the end that it's easy enough. Once it's been put into practice on one site, someone will copy it inevitably. So they now see the unique selling point as the configuration tool and the certification, and actually the contractor is willing to license the production of the products themselves to others with manufacturing facilities. The intention is to sort of make that open competitive playing field of others being able to manufacture the system as long as they're in accordance with the conditions of the certification.
Thank you. Next question. How can this approach incorporate architectural design or site-specific responses with aesthetic value too?
Do you want to take that one, Gbenga?
Yes, thanks, Mungo. Thanks, Sharon. Well, that's a very good question, because at the start of the development of the shells, we did have the conversations around what will the surfacing look like, and can we change the aesthetics in the sense that would you have different surfaces for different faces of the shells to ensure that you have like a gritted look, or do you have some gravel look? But different aesthetics look anyway were considered. And in conversations with HS2 as well, because of the common design elements and needing to be consistent across the entire project, and also relevance to the specific areas that the structures could be located, there is a potential and possibility of having the surfaces of the shells, because they're all precast in a manufacturing plant, to have that facility to create different surfaces, different looks, and different aesthetics feels to be specific to the structure. But the shell in itself does not change, but the look itself does. And there were conversations around, do we just have a single box? Can we have circular shells as well to have that sort of curved look with piers? But all those were conversations that we felt we'll start with the box first and see how that progresses, and then we can later on add different elements. But it's all the pre-manufacturing process, and also the product-led delivery. So if there is the scope and market for that sort of product, then it will be brought online.
Thank you. Are there any rail bridges constructed so far using this method?
And Gbenga, I think you touched on this in one of your initial slides. Yeah.
Yes, so I mentioned the East-West Rail Line, which is a line between Oxford and Cambridge, and it crosses the West Coast Main Line. So it's currently been constructed at this point in time. Thank
you. If you can clarify, to what level of completion of design does your modularization take the design? Is it conceptual, is it preliminary, or even final design?
Angel, do you want to take that one?
Yeah, short answer is concept design. So feasibility study, it does not undertake a full detailed design.
And if I can just supplement that, so one of the objectives of developing the configuration tool was to try to open the market to the offsite solution. One of the barriers that we had observed on other projects was you would tend to have a traditional in situ option. The problem with the offsite products is they tend to be specific to a particular manufacturer or system. So it then becomes very difficult, if you want to have a tendered solution open to the market, to have a particular modular solution. So the intent of the configuration tool is actually, when it then does come to the time of putting a price to it, actually if you, in the space of half a day, or actually the tool takes less than half an hour to run from start to finish, if you can have a completed general arrangement drawing, a set out of how the modules might look and the cost, then it becomes very easy to quickly compare that offsite solution compared with the traditional solution. So it was all about opening the doors to having the offsite solution.
Thank you. How did you ensure the long-term integrity of the joints between the units? Water can travel a long way on horizontal joints, for example, the cover slide visual.
Do you want to take that one, Gbenga?
Yeah, so the shells themselves have gaskets at the base, so that when they are arranged vertically, that is sealed by gravity. And then after construction, we have sealants on the vertical faces as well to prevent water ingress.
And I guess also critically, the concrete mix for the in situ cores has been specified such that it doesn't rely on any enhancement due to the presence of the precast concrete around. Clearly, the critical sort of durability feature is where you have the joints. So the reinforcement design and the mixed design is assumes that there is no additional protection from having that surrounding concrete.
Thank you. We have here a comment and a question. The comment is, the use of concrete from formwork must end up with a greater quantity of concrete than in situ abutments cast in traditional formwork. How can this provide a consistent carbon saving?
Well, we actually did carry out carbon assessments on page 2. We looked at the typical structure that we'll have and the final product with the shells. And while you had volume in terms of concrete due to the cores being larger, in terms of the rapid construction, you save time, or rather you save the carbon in terms of transportation, you save carbon in terms of the formwork that is being put up and then dismantled and then could be either thrown away rather than being reused. So it's all about the offsets between what you have traditionally and what you're going to have with this particular format. And also the concrete that is used within the cores themselves do not need to be the typical high carbon cement content concrete. You can use low carbon cement concrete in there as well to offset that.
And it's interesting, it's kind of a similar response both for carbon and cost, both of which we sort of had challenges on when people were initially introduced to the system. You know, the response for cost is very similar, that you know, the capital costs are probably similar, but the saving is in the time saving and the indirect costs, and also the risk reduction associated with having the predictability of putting the system together.
Thank you. We have many, many more questions. Apologies if we're not going to go through them all today. It will all be answered by email. The last question that I will take is like this. You mentioned the possibility of integrating carbon and circular economy, sustainable resources management modules within the process to help quantify certain environmental savings. Can I ask what your planned approach to this and the expected timescales?
Great. It's probably best if I take that one, as it sort of touches on the future direction for the tool. So clearly what we've just described was a particular project undertaken with specific funding from Highways England and innovation funders, which is now complete. What we're currently in discussion, both with that funder, Highways England, and with Laing O'Rourke as the owners of the system, is future enhancements to the configuration tool. So at present, we don't have a definite plan for when that will happen, because we're waiting on those funding and project opportunities to make those improvements. But that certainly is one of the areas that we'd like to build into the future process. Equally, if I look internally to WSP, so I talked about the intellectual property of the system residing with the contractor, but the intellectual property of the parametric tools, which Angel described, residing with WSP. So certainly within the UK, we've got a very strong drive towards net zero at the moment. We've publicly set our target to reduce by 50% in the next 10 years, the carbon associated with our design and advice. And some of the work streams that we have internally at the moment are looking at exactly how we take those carbon tools and how we start building those into our design as usual processes. So we're still at early stages of that, but we certainly see a transfer of that carbon measurement moving from traditionally, we pass the details over to our sustainability teams. We see that now moving in to become part and parcel of the normal design work, subject of course to appropriate tools being available and appropriate training. We're also setting up a network of our subject matter experts, for example, looking at driving WSP's response towards low carbon concrete, low carbon steel, looking at timber structures, just putting that out there as well, looking at low carbon earthworks and the ways that we can overall improve the construction process from the point of view of carbon.
Fantastic, thank you. So we're at the end of our webinar session. Please feel free to follow up directly with Mungo, Gbenga, and Angel via the contact details shown on the screen. And I would like to thank all attendees for joining today, and a big thank you, team, for a fantastic presentation. Thank you so much.
It's been really good to talk to you all.
Thank you very much. Have a wonderful day. I will wrap up the webinar now. Thank you.